Hello, my name is Robert Smith and I'm with New River Community College's Academic Assistance, and today we are discussing redox reactions. We're given the task to classify each of the following redox reactions and which species is the oxidizing agent and which is the reducing agent. So to classify it means that we're going to determine what kind of reaction we are dealing with. In our first example, we have two species that are combining to form a third species in the product. So this is called a combination reaction. Also called a synthesis reaction if it ever comes up. The trickier component to this process, is to determine what is the oxidation and what is the reducing agent. In order to do that, we need to assign oxidation states. One of the rules for assigning oxidation states is any element in its natural state will not have an oxidation number, or rather its oxidation state will be 0. So diatomic oxygen is naturally occurring. That's how it naturally forms. It does not form as monatomic or triatomic. It's always or usually diatomic. It can occur in other cases, but that is its naturally occurring state. Same is true for hydrogen, diatomic hydrogen. So our oxidation states for each of those is 0. So then the task becomes to assign the oxidation states for the other components of this reaction, and that's water. Well, we know that hydrogen attached to a nonmetal has a +1 oxidation state, and we know that oxygen, unless it's a peroxide or superoxide, has a -2 oxidation state. And that actually shows up here. So this is +1 and that's -2. And it makes sense because there are two hydrogens, so that would make it a +2 overall oxidation state, and one oxygen, which is a -2. The +2 and -2 cancel each other out. And because there's no charge on water, it makes sense that those would be the oxidation states. So from there we can determine what is being reduced and what is being oxidized. And you determine what is being reduced if the oxidation state or oxidation number is decreasing. So this, our oxygen, is being reduced. I'm going to put an R there for reduced. And our hydrogen is being oxidized, because the oxidation state is increasing. The trickiest part in assigning what is the oxidizing and what is the reducing agent is to determine that the trickiest part in determining what is the oxidizing versus what is the reducing agent is that it doesn't correspond with what is actually happening to the species. So it's actually just the opposite. So if something is being reduced, it is in effect oxidizing its counterpart. And if something is being oxidized, it is in effect reducing its counterpart. So even though oxygen is being reduced, it is also acting as the oxidizing agent. Similarly, while hydrogen is technically being oxidized, it is also in effect acting as the reducing agent. I know it's a kind of a weird concept, but just think of it as the opposite of what is actually happening is its agency. So you determine what is actually happening in the reaction, and once you determine that, you then take its opposite for determining what the agents are. So if something is being reduced, it's actually oxidizing something else, therefore it is the oxidizing agent. If something is being oxidized, it is actually reducing something else, and therefore it is the reducing agent. Let's look at another problem. We know that our oxidation states for our naturally occurring compounds are going to be 0. And it also makes sense, because if oxygen, diatomic oxygen, has no charge on it, so its oxidation states have to equal 0. If oxygen was a -2, as it normally is when it's not an oxide, and when it's not a peroxide or superoxide, then this O2 would have an oxidation state as a -4, and that simply doesn't make sense for that molecule. So you can look at it either, you can just recall that it is the naturally occurring diatomic molecule that has an oxidation state of 0, or you can just say that it wouldn't make sense to assign a -2 to it. However, we can say that the NO2 has a -2 for its oxidation state on oxygen, and because there are 2 of them, it actually has it would count as, the oxygen counts as a -4, so our nitrogen has to have a +4 on it in order to cancel out with the oxygen, because there are 2 oxygens and 1 nitrogen. Nitrogen is +4, -2 for one oxygen, -2 for another, so 4 - 2 is equal to 0, that's what we want. So let's identify, before we continue with determining the oxidizing agent and the reducing agent, let's take a moment to identify what kind of reaction we're actually looking at here. Well, we're taking a larger molecule and breaking it up into its simpler parts. That is called a decomposition reaction. And doesn't have another name, it's simply decomposition reaction. So getting back to the determining what is the oxidizing and what is the reducing agent, you'll note that on our NO2 that the oxygen is increasing from a -2 to a 0. So the oxygen is oxidizing. Conversely, the nitrogen is dropping from a +4 to a 0, so it is reducing. Therefore, we can say with confidence that nitrogen is reducing therefore it is the oxidizing agent. Oxygen is oxidizing in this case, though not always. Therefore, it is the reducing agent. Let's look at another example. Identifying what kind of reaction this is, it takes a little bit of expertise, but it's not too complicated. Whenever you have a hydrocarbon being burned with oxygen, it is produced, and it produces CO2 and water, it is automatically classified as a combustion reaction. So that is the type of reaction that is being processed here. So we have several things we need to assign oxidation states at this point. We know that our O2 is going to have an oxidation state of 0. We can also assign our oxidation state on the hydrogen on the hydrocarbon. Because it's attached to a non-metal, it would have a +1. And over here, we'll just write it out. There are 2 of some value plus 1 times 6 is 6 equals 0. So 2x has to equal -6. X is equal to -3 when you divide out. So our carbon has a -3 oxidation state. Over on the other side, we know that hydrogen on the water is going to have a +1, and we know that the oxygen on the water is going to have a -2. We know that the oxygen on the carbon dioxide is going to have a -2, and there are 2 of them. So back over here, we can do another little calculation. We have x plus -2 times 2, so -4 is equal to 0. So x has to equal 4, because you would just add 4 to both sides to isolate x. So our carbon on this side, on the product side, is 4, positive 4. And now we just need to look and see what is being oxidized and what is being reduced. So note that our oxygen in 2 different places is going from a 0 to a -2. So it is most definitely being reduced. Other species involved are hydrogen, but hydrogen is a +1 on both sides. So it's not doing anything. It's neither being oxidized nor being reduced. However, our carbon is jumping from a -3 to a +4, which means that it is definitely oxidizing. So we can say with some measure of certainty that our oxygen is being reduced. Therefore, it is the oxidizing agent. And carbon is being oxidized therefore it is the reducing agent. Let's do one more. First, let's identify what kind of reaction this is. You'll have to go into your book and look at this, but this is basically a displacement reaction. And the type of displacement is identified by what species is actually being displaced. And in this case, it's hydrogen. You're breaking hydrogen off and replacing it with something else. Hydrogen is a product, therefore it is called hydrogen displacement. a hydrogen displacement reaction. Next, let's go ahead and assign our oxidation states. So calcium all by itself is going to have a 0. Likewise with diatomic hydrogen, it's going to have a 0. So now we just have to assign everything else. We know that hydrogen, whenever attached to a nonmetal, is going to have a +1. So that means that in this case, chlorine has to be a -1. We know that calcium, because it is a group 2 element, will have a +2 oxidation state when attached to another element into a compound. Therefore, chlorine has to be a -1 again, because there are 2 chlorines, and in order to make the charge equal 0, the oxidation states have to equal 0. Calcium is +2. There are 2 chlorines at -1 apiece. Therefore, chlorine and calcium cancel each other out. Therefore, with some certainty, we can determine that calcium is being oxidized because its oxidation state is increasing, and hydrogen is being reduced because it's going from a +1 to a 0. Chlorine has the same oxidation state on both sides. Therefore, it doesn't actually do anything in terms of oxidation reaction. So, we can then determine that our hydrogen is being reduced and is therefore our oxidizing agent. And calcium is being oxidized therefore it is the reducing agent. And that's all there is to it. Please note that there's no oxygen involved in this reaction whatsoever, so determining whether something is oxidized or is the oxidizing agent, conversely, has nothing to do with the existence of oxygen. It is a term to determine the oxidation state of the species involved.